Hello students, welcome to our channel physics class, and today we will study about Earth's magnetism. It is a very interesting thing because we want to study about the magnetism that exists in our own Earth, because Earth acts as a giant magnet and there is magnetic field at the Earth's surface. And what is the order of magnetic field at the Earth's surface? If you want to know, then at the Earth's surface, our own Earth, at the surface, the magnetic field varies from place to place. So if you take the average value of the magnetic field at the Earth's surface, then it is around 10 to the power minus 5 Tesla. Yes, this is the magnetic field that exists on the surface of the Earth. Then where does this magnetic field comes from? We consider the Earth's magnetic field to be like a bar magnet. But it is not actually a bar magnet. It is actually produced due to the electric currents produced by convective motion of metallic fluids of molten iron and nickel. Since we know that inside the Earth the temperature is very high and there are ferromagnetic materials like iron and nickel which have the magnetic property. So due to their movement, due to the movement of these metallic fluids of molten iron and nickel, there is a current due to the movement of the Earth. And due to this current, this magnetic field is produced. And this effect we call as dynamo effect. And this is the best known theory till date. Although the research is going on, but for the day, this is the best known theory. So we consider this effect called as dynamo effect as the best for the existence of magnetic field within the Earth. Then why we consider Earth as a magnetic dipole? Because if you look at the magnetic field lines of Earth, then these magnetic field lines of Earth resemble like of a magnetic dipole. So we consider it as a magnetic dipole at the center of the Earth. Actually, there is nothing like a magnetic dipole inside the Earth, but if we look at the magnetic field lines, then these resembles to the magnetic dipole, and that is why we only consider that there is a giant magnetic dipole in the center of the Earth. And the axis of this dipole is tilted by 11.3 degrees with the axis of rotation of the Earth. Now, what are the magnetic poles? Magnetic poles are those places where the magnetic field lines due to dipole enter the Earth and leaves the Earth. So the field lines go to the north magnetic pole and comes out from the south magnetic pole. So if you draw the diagram of our Earth, now this is the north magnetic pole and this is the south magnetic pole. Because here we can consider as a magnetic dipole at the center, you can consider actually it does not exist, but due to the properties of the magnetic field lines, we consider it as a magnetic dipole. So it is in magnetic north and here is the magnetic south. And if you see the geographical north pole and south pole, then these are like this. This is the geographical north pole. And this is the geographical south pole. And the circle that passes from the center of the Earth, that is the middle cross section of the Earth, is known as the equator. So if I want to draw the equator, I'll draw it like this. And this equator divides the Earth into two equal halves according to the north and south pole, geographical north and south pole. And if you go to the magnetic north pole and south pole, then you can also draw a magnetic equator. So the green one is our geographical equator and the blue one is our magnetic equator. Because if you see Earth from this magnetic north pole and magnetic south pole, then this will be the middle cross section shown in blue. So this we call as magnetic equator. So this blue one is our magnetic equator And the green one is our geographical equator. And this our axis of dipole is tilted by 11.3 degree with the axis of rotation of the Earth. It keeps on changing, but that is very slow. It takes millions of years, so you can also remember always that it is tilted with an angle of 11.3 degree. So these are the points that are the basics of the Earth's magnetic. Now, if you want to have a realistic view of our Earth behaves as a magnet, what are the magnetic field lines? Then inside the core of the Earth, it is a high temperature, so there are ferromagnetic materials which are in the molten states, and due to the motion of the Earth, there are current produced, and due to this current, the magnetic field is created, which we call as a dynamo effect. So if you want to have a real view of this, then we are giving you a small clipping. Just look carefully into this clipping and know more about the Earth's magnetic field. Just observe it with your eyes. Earth is a gigantic magnet with a magnetic field that stretches into space. Recently, researchers have created a model of what Earth's magnetic fields look like. And the slightly faster rotation sets up the magnetic field. This field emerges from Earth at one pole and returns to the opposite pole. The poles are where the strongest magnetic forces are located. Earth's magnetic poles are some distance away from the Earth's actual geographic north and south poles, and the positions are very slowly shifting. Earth's magnetic field is similar to the magnetic field of a bar magnet. The magnetic field is created by the movements of electrons roaming around the nucleus of an atom. A single atom by itself will have a very strong magnetic field. However, the magnetic fields of billions of atoms can combine to form a low, powerful magnetic forces. This animation shows the ball that represents an atom. The red half of the ball represents one magnet pole, and the white half represents the opposite magnetic pole. The cluster of balls represent what happens when billions of atoms line up in the same direction, which forms a strong magnetic field. When magnetic fields are aligned up in the same direction, just like the magnetic field of these balls, they create a magnetic domain. All of the material's magnetic domain in the material are aligned up in the same direction, then the material will have a very strong magnetic field. Now think about our Earth. It has a very high temperature inside. Its liquid iron core and the solid core are made mostly of the ferromagnetic materials such as iron and nickel. Earth too can form magnetic domains. How does this happen? One possible explanation is that the magnetic field forms as a result of movement of Earth's liquid iron core. The field extends to Earth's mantle crust and into thousands of kilometers in space. So after this clipping, we have seen what is the dynamo effect, electric current produced by how the metallic fluids, they make a dynamo effect. That is the best known theory till date. We have seen the magnetic dipole, how Earth behaves as a giant dipole. We have also seen the pictures of magnetic poles, magnetic north pole and magnetic south pole. We have seen a clear view of the magnetic field lines and how this field lines enters from the north magnetic pole and comes out from the south magnetic pole. We have also seen that how this magnetic north and south pole, this axis is tilted with the geographical axis. So let us move further. After having this clear view of the Earth's magnetic field and magnetic Earth, just clearly visible what we have seen in the clip, now we go to certain theory regarding this, and that is also much interesting. Study about magnetic declination. So let's draw our Earth. This is our geographical North Pole and South Pole. G suffix I am writing for geographical. Then if you draw the magnetic North and South Pole, then we can draw it like this. So these are our magnetic North Pole and South Pole. Now first thing we define is magnetic meridian. Now what is this magnetic meridian? Magnetic meridian is nothing, it is a vertical plane. Always remember this meridian is a vertical plane. And this plane is passing through the imaginary lines joining the magnetic north and south pole. So if you join the magnetic north and south pole and you draw a vertical plane, then this vertical plane is known as magnetic meridian. So here we have a blue line joining this magnetic north pole and south pole. So if we take a vertical plane which is passing through this imaginary line, then this vertical plane is our magnetic meridian. So if you see the plane, a vertical plane which is passing through this magnetic north and south pole joining line, then this vertical plane will be a circle, obviously. So this circle is like a longitude, as you know, because we have studied geography in our earlier classes, then we have longitudes and latitudes. So if you take the vertical plane, then it will be a circle just like a longitude. Now what we do, we take a magnetic needle, that is a magnetic compass we use. All of us must have used magnetic compass to find out the direction that always point out in the north and south direction. So we are taking a magnetic needle or a magnetic compass and we are allowing this needle to swing freely horizontally. So this is able to swing freely in a horizontal plane. Then it will always line the magnetic meridian and the north pole of magnetic points in the magnetic north pole. That means if you take a compass and if you allow it to swing, then it will always line this magnetic meridian. That means the axis of the compass will be always along the magnetic axis. And the north pole of magnet points in the magnetic north pole and the south pole will point out in the magnetic south pole. As simple as that. And this magnetic meridian we have studied. Similarly, we can define a geographic meridian. So this geographical meridian will again be a plane, a vertical plane, which is passing through the imaginary line joining geographical north and south pole. So with this green line we have shown, and this is a geographical north pole and this is a geographic south pole, and we have drawn this green line joining these two poles. So if we draw a vertical plane which is passing through this line, then this vertical plane is known as geographical meridian. So since you can see that these two lines are at some angle, so the vertical planes drawn through these two lines will be also at some angle. So we can say that the magnetic meridian is making an angle with the geographical meridian. And this angle is shown by a compass needle. This angle we call as magnetic declination. So the angle between the magnetic meridian and the geographical meridian, which is shown by a compass needle, is known as magnetic declination. So this angle is called a magnetic declination, the angle that the magnetic meridian is making with the geographical meridian. Now we know what is the magnetic meridian, we know what is the geographical meridian. Vertical plane, two vertical planes, and the angle between these two vertical planes which we measure from a compass needle is called magnetic declination. So how will we show this magnetic declination? Just draw a simple diagram to show the magnetic declination. Just draw a vertical line. This is our actual north, geographical north, and this is our actual south. So we have shown our actual north and south poles with this vertical line. And if we allow our compass needle to freely swing, then it will always point in the magnetic north and south pole, that is in the magnetic meridian. So if we draw a compass needle in the magnetic meridian, that is in the vertical plane of this blue line, let us draw a compass needle. then this angle you see between them is magnetic declination. So we write it here as declination. So this is how beautifully we can show magnetic declination. I hope it is very much clear to you what is magnetic meridian, what is geographical meridian, what are these two vertical planes and the angle between these two vertical planes, and why our compass needle is declined, and this angle is known as a magnetic declination. That easy that is, and so much interesting because it is related to our own earth. Now one more thing we want to study, and that is angle of dip. Now we know magnetic declination and we want to know the other thing, that is angle of dip. Let us see what is this angle of dip. Angle of dip is that angle that our total magnetic field of the earth makes with the surface of the earth. So the angle between the total magnetic field of the earth and the surface of the earth is called angle of dip. So let us draw our earth. So this is our earth and somewhere here is the center. Somewhere here is the center, and here I am showing a magnetic north pole. And we take the magnetic meridian, that is the vertical plane which is passing through north magnetic pole and south magnetic pole. So we take any point P. This is any point P on the magnetic meridian, and this point P is on the surface of the earth. This plane we have taken as a section through the earth. This is just a section of the earth. We have cut it like this. So here we want to calculate the total magnetic field due to earth. So this is the total magnetic field due to earth. Then if you want to take the horizontal and vertical component, then the horizontal component this is the horizontal component. So we are denoting it as horizontal component of Earth magnetic field HE. And the vertical component we are showing it as ZE. So ZE is the vertical component of the Earth's magnetic field. And this angle will be the angle of dip. This is an angle, so we can call it theta, but here mostly in the textbook it is given as I, so I is the angle of dip. So we can say that the angle between the Earth magnetic field, the total Earth magnetic field, which is given as BE, so the angle between the total magnetic field of the Earth and the horizontal component of the Earth magnetic field is angle of dip. So how we have written the horizontal and vertical component, if you want to know, then the Earth's total magnetic field is BE. And if you want to take the horizontal component, that is written as HE, that is the horizontal component of the Earth's total magnetic field, then this angle is I, so this will be BE cos of I. And if we want to write down the vertical component of the Earth's magnetic field, ZE, then if this total angle is 90 degree, because if you take the horizontal and vertical component, then this total angle is 90 degree. So this is I, so this will be 90 minus I. So if this component is cos I, then cos 90 minus I is sin I. So Z is equal to BE sin of I. That is how we take the horizontal and vertical component, where the angle is makes the cos of angle and the other side is 90 minus angle, so it is always sine. So H is BE cos I and Z is BE sin I. So the angle between the horizontal component and the total magnetic field is known as the angle of dip. And if you want to know the value of angle I, then here you have cos I and sin I. So easily you can calculate the tangent of I, that is tan I, that gives us the slope. So tan I will be ZE upon HE. And if you want to calculate this angle of dip I, then you can take tan inverse of ZE upon HE. So that is how we calculate the angle of dip. Now if we draw our Earth once more. And this is with North Pole and South Pole. And here we assume a large bar magnet that is placed inside. So if you draw the magnetic field lines, it would be somewhat like this. So if you place a magnetic compass needle over here near to the North Pole, then it will be shown as like the North Pole of the dip tilts downwards. So here will be the North Pole and this will be the South Pole. So the magnetic compass needle, you can place it anywhere on the surface of the Earth. So if you place it near to the North Pole, here we have shown as the North Pole, and if you place it here, then the North Pole will be always downward here. North Pole will be here, because if you see the magnetic field lines, they are going downwards, so our North Pole will also be going downward. That means if you're standing here, if you are the observer and you are standing here, then your North Pole is downward. So here, standing here, you will have a North Pole in the downward direction. Now come to the other pole. So if you place a compass needle over here, then our magnetic field lines are going in the upward direction. So this will be our North Pole and this will be our South Pole. So if you are as an observer standing here, so your South Pole will be downward. That means the South Pole will be in the downward direction and the North Pole will be in the upward direction. So this way, anywhere on the surface of the Earth, you can find out the direction of compass needle. Say for example, I place my compass needle over here. So you see that magnetic field lines are going upward direction. So this will be the North Pole and this will be the South Pole shown by the compass needle. So that is how easily you can use a compass needle. So here what we have to note down, that if this is our equator, then we divide the Earth into the two equal halves. This is the northern hemisphere and this is the southern hemisphere, two equal halves. So we can say that in the northern hemisphere, North Pole of the dip needle tilts downward, and whereas in the southern hemisphere, the South Pole of the dip needle tilts downwards. So always keep in mind. So always keep in mind the same. Studies magnetization and magnetic intensity. So magnetization we always represent with the symbol capital M, that we may use for magnetic moment also. But remember, capital M is for magnetization. If you are using, then you can replace magnetic moment with small m. So magnetization is always shown with capital M. Now what is this magnetization M? This is the net magnetic moment per unit volume. So if you divide our magnetic moment, now we will show it with small m, otherwise both will be capital M. So mind this thing, now we are showing our magnetic moment with small m. And we divide it with the volume. So the magnetic moment per unit volume. And which magnetic moment we have to take? Say if you are dealing with a system, then you have to take the net magnetic moment. So if we take the net magnetic moment and we divide it with the volume, then we will have the magnetization. So the definition of magnetization is the net magnetic moment per unit volume. Now if you want to know about the units, then this magnetization is magnetic moment, that is the net magnetic moment, and you have to divide it with the volume, and you know the formula for magnetic moment. This is I into A, that is the current into area, and this is the volume. So the unit of current is always ampere, and area will be in meter square, and your volume will be in meter cube. So this meter square cancels out here and we are left with 1 meter. So this is ampere per meter or ampere meter inverse. So the unit of magnetization is always ampere meter inverse. Now let us be more clear about what is this magnetization is. So we take some magnetic material, that is magnetization due to some flow of current. So for example, we take a solenoid. So this is how we draw a solenoid, that we have a hollow cylinder and here we have a number of turns of wires wrapped and the current is flowing through this. So this is a simple representation of a solenoid. And this we take the axis of the solenoid. And the magnetic field due to solenoid we know as always B is equal to mu naught and I. Mu naught is the magnetic permeability in the vacuum, small is the number of turns per unit length, and I is the current. Now we take it as a hollow cylinder. So if we take it, there is material of non-zero magnetization. That means we have some material which is a magnetic material inside the solenoid. Then this magnetic field will be increased. So this is the initial magnetic field. So we denote it with B naught. When there is no magnetic material, this is a hollow cylinder. That is, now we are studying till now. Then that is the reference magnetic field. B naught is mu naught Ni. Now what we do, that inside the solenoid we placed a magnetic material. So if there is magnetic material inside the solenoid, it will also get magnetized. So now the total magnetic field will be the sum of initial magnetic field plus the magnetic field due to that magnetization material. This is our initial magnetic field of a solenoid and this is due to the magnetic material we have inside the solenoid. Now the magnetic field due to this magnetic material will depend on magnetization of the material. So this magnetic field is directly proportional to the magnetization of material. So in order to remove the proportionality sign, we introduce a constant, and this constant always in magnetic field or magnetization is always mu naught. So we say that this magnetic field due to magnetization is equal to mu naught m. Mu naught is a constant whose value is 4 pi into 10 to the power minus 7. We already know. And if you want to go to the details, you can refer to our lecture. The links are given below. And here mu naught is the permeability of the free space or vacuum. So this is the relation between the magnetic field due to magnetization and magnetization. And also if there is some magnetic field intensity, then that is also added into this term. So we write down this magnetic field due to magnetization will be the sum of this mu naught, and we add this magnetic field intensity into this magnetization. So Bm is equal to mu naught m plus h. So from here we can calculate this h. H is the magnetic intensity or the magnetic field intensity. So this magnetic intensity or magnetic field intensity, full name is magnetic field intensity, but normally we call it magnetic intensity, and it is represented with the symbol h. So from here, if you calculate the value of h, then h is equal to B upon mu naught minus m. So from here you can see that If you equate the units of both the sides, then the magnetic field, and here is a magnetization, and this is magnetic field intensity. So these two are in addition. That means the units of magnetic field intensity should be similar to that of magnetization. So we can say that the magnetization and magnetic field intensity H has same dimensions. Now, what is the relation between this magnetization and magnetic field intensity? Let us find out. This magnetization is proportional to the magnetic field intensity. And again, to remove this proportionality sign, we have to introduce this much. We have to introduce a constant, and this time we cannot use mu naught because we have already used mu naught. So we introduce a new constant that is known as xi. So this constant is xi and h. This is known as magnetic susceptibility. Mu naught is the magnetic permeability and xi is magnetic susceptibility. So this relation between magnetization and magnetic intensity. So these are the two important relations we have to always remember whenever you are studying about magnetization. So these two relations you should always remember. Now this is magnetic susceptibility. It has different values for different type of magnetic materials. We will go into the details of magnetic materials. The main categories, we can divide them into paramagnets, and dimagnets. So for all these three types of materials, this magnetic susceptibility has different values. It has a high value for the highly magnetic materials, and it has a negative value for the non-magnetic materials, or which are not attracted towards the magnetic field. So we will have a quick look of how xi varies for different materials. So in broad, we consider three types of materials. The most important magnetic materials are all ferromagnets, which are strongly attracted towards the magnetic fields, and they have high magnetic properties. We call them as ferromagnets. We'll study them. But for now, we are just studying the value of xi. So that is a brief introduction. Then comes the paramagnetic materials. So these paramagnets also have magnetic properties, but slightly less than in comparison to ferromagnets. And the third type is dimagnets, which are not attracted towards the magnetic field. So for paramagnets, xi will have the highest value, it will have the positive value, and all the large values because these are highly magnetic. For paramagnets, xi will be positive because these are attracted towards the magnetic field, but this is small in comparison to the ferromagnets, so the value will be small. And dimagnets are not attracted towards the magnetic field, so xi will have negative value and small. So this is how it is easy to remember. The xi for paramagnets is positive and large. Paramagnets is also positive but small. And dimagnets, it is negative and small. So we have just derived the relation between the magnetization and the magnetic field intensity. So if you write down for dimagnets, then this will have a negative value. So m is equal to minus xi of h. That means for dimagnets, m and h, magnetization and magnetic field intensity are in opposite direction. Then what for paramagnets and paramagnets? They will be in the same direction. So formula m plus h. So we can substitute m is equal to minus xi h. We can write on b is equal to mu naught xi h plus h. So b is equal to mu naught, h we can take as common. So this is 1 plus xi. So if it is either a paramagnetic or ferromagnetic material, then we can write down this as h plus xi h, because m may be written as xi h. Now in this equation, we can take mu naught and h as common. So this will be 1 plus xi. And 1 plus xi we can write down as mu r, that is a relative permeability. So this is mu naught, and this we can replace as 1 plus xi we can replace as mu r, that is the relative permeability, mu r, and this is h. So this relative permeability is the ratio of the permeability of any material to the permeability of space. So mu naught into mu r you can write down as mu. So B is equal to mu h. Whenever you are having any magnetization material, then B is equal to mu h. That is again the relation we have already derived, but it is very important. And if you want to know B in terms of h, you can use mu h. And contrary, if you want to know h in terms of V, then h is equal to B upon mu. That will be very much helpful in solving your numericals, because till now we have calculated the magnetic field very easily using the Biot-Savart's law or Ampere's circuital law. If you want to know the numericals, I have given the link in the text. I have given the link below, so you can go to that and you can do the numericals. So say for solenoid we were considering, so we know the magnetic field B, so we can do H is equal to B upon mu. Let us see how. So we have just derived H is equal to B upon mu. So for a solenoid, if you are having some magnetic material, then it is B is equal to mu N I. And if you want to know H, then this is equal to N into I. So for a solenoid, if you want to know the magnetic field intensity, then H is equal to Ni. Whenever we place a magnetic material inside this, then B is equal to mu naught Ni and H is equal to Ni for a solenoid. See, it is that easy to calculate if you know the formula. So that's all for today. If you like this lecture, then like and share and subscribe to our channel Physics Class so that you can continuously receive notifications for more such interesting lectures. Thank you.